Okay, here we're going to finish up electrochemistry. This is the exciting part where we get to connect electrochemistry to thermochemistry to equilibrium. So the spontaneity of redox reactions is governed by this equation. So the relationship between delta G, or Gibbs free energy, and electrochemical cell potential is right here. Delta G equals negative NFE. I like to think of this to remember the equation as delta G is no free energy, because there's negative no free energy, right? If you're into that, great. If not, you're like, dude, Mr. Wolf, I have it on an equation card. I'm fine with that. That's fine. If you want to see the derivation, how that is derived, please feel free to click here. I'm not going to go over it, but that's where it is. F stands for Faraday's constant. That is 96,500 coulombs per mole. That's per mole of electrons. This is the N, the mole here, is the mole of electrons transferred in the electrochemical cell. So if it's a one electron transfer, one electron goes from the oxidized chemical to the reduced chemical, then that number is 1. If it's 2, 3, 4, so on and so forth. And then that also equates into 96,500 joules per volt slash mole. Volt dash mole. So volts and moles are being multiplied by each other in the denominator. And that's how you get energy term in joules or kilojoules from an electrochemical cell potential in volts. Okay, Faraday's constant is the conversion factor. So here's a little simple calculation. We're going to determine whether reactions are spontaneous or not. And so you're going to try to figure out in this one, is this going to be spontaneous, right? And so to determine, you can look up the cell potentials of copper being oxidized to +2 and then hydrogen being reduced to 0. Okay, and we know the E0 reduction for hydrogen is 0, so it's all going to depend upon the oxidation of copper, right? And then we have this one where you have chlorine being reduced to chloride and iodine being oxidized to, or iodide being oxidized to iodine. So if you look, you have the E0 reduction for copper is 0.34, and so it is the reduction minus the oxidation, right? 0 volts minus 0.34 volts, so that would be negative 0.34 volts. And since it is a negative cell potential, that means if we plug that into delta G0 equals negative NFE0, right, you're going to get a positive value for delta G, and then that means the reaction is non-spontaneous, right? So choice A would be non-spontaneous. And then we go to choice B, we have the chlorine in a different slide. No, here it is, down here, sorry. Can't point to it or else the slide thing pops up. So the reduction is positive 1.36 volts. The oxidation is positive 0.54 volts. So the reduction minus the oxidation, or the cathode minus the anode, gives you 1.36 minus 0.54, so it's positive 0.82 volts. So that reaction is spontaneous and it will happen. And so just like delta G and delta G0 are related, the values of E and E0 are related, and we can substitute in here and get our relationship between the reaction quotient, or the concentrations of products over reactants, and how that can affect your cell potential, right? Because the standard cell potential is assuming, of course, that you have 1 molar solutions, right, of everything, and everything's standard, right? What if it's not standard, right? So then you can calculate your cell potential based upon if it's not at standard conditions by substituting in E for delta G, right? So negative NFE, and then if you do some math, fun stuff, you get E equals E0 minus RT over NF times the natural log of Q. For some reason, chemists don't like natural logs, and if we can avoid natural logs and convert them to base 10 logs, we do. And so that's what this is. This is the conversion factor for from natural logs to base 10 logs. You do that, and then you just do the math of RT over NF, and as long as you're at 298 Kelvin, you can do that, and then it just matters about the moles of electrons, right? And so then this tells you your conversion factor between your cell potential at ideal conditions and then your cell potential at real conditions, whatever the real concentrations of products over reactants is. And so if we use this as an example, we have a standard zinc and copper cell. We previously determined that the cell potential for this is 1.1 volts, right? And so what happens if you have a zinc ion concentration of 2 molar and a copper ion concentration of 0.5 molar? What does that do? Well, you'll notice that the zinc ions are on the product side and the copper ions are on the reactant side. And these guys are solid, so they're not factored into our Q calculation, right? Our calculation of the reaction quotient. And so we take the 2 molar, the concentration of zinc, divided by 0.5 molar, the concentration of the copper, and you get 4, right? The ratio of zinc to copper. Then you take the log of 4 and multiply that by 0.0592 volts divided by 2, and then subtract that from 1.1 volts, and you get 1.08 volts. So you notice that this is a less spontaneous reaction. You get a lower voltage, but the converse would be true if you were able to change these around. If you had a 0.5 molar zinc solution and a 2 molar copper solution, then you would increase the voltage, right? So there's ways to maximize voltage in an electrochemical cell, and you could do that by changing concentrations. So you can also create a battery just based off of concentrations. And so if you had the same reaction on both sides, right? You have nickel and nickel ion solutions. So nickel going to nickel 2 plus, and then nickel 2 plus going to nickel, right? I'm sorry, the other way around. Nickel 2 plus going to nickel, and nickel going to nickel 2 plus. All you could do is separate them with a salt bridge and put a voltmeter in there. You can actually get a measured voltage from this, right? Because E equals E0 minus 0.0592 volts divided by the moles of electrons times the log of Q, right? Well, the Q in this case would be the concentration of the anode over the concentration of the cathode, right? And so our concentration of anode is 0.001, and the concentration of our cathode is 1. And so the Q is equal to 1 times 10 to the minus third, right? The 0.001, because something divided by 1 is the same number. And so when you put that in there, you can get a positive cell potential from a concentration cell. So this is a very exciting application. So if you're ever stranded on a desert island and you need a battery, you can just differentiate salt concentration in solutions, connect a salt bridge and some metal to it, and then boom, you've got a concentration gradient cell. Not to say that you'll ever be stuck on a deserted island or anything like that, but you could do it. And then the rest of the chapter is not necessarily terribly vital, but it's filled with handy information. So this is a cross-section of a lead-acid battery. This is found in most automobiles, right? All of the automobiles that I can think of off the top of my head, but I am a scientist, so I have to just say most. This is using lead and lead oxide as your cathode and your anode. And it is a very reversible reaction, so you can easily recharge a lead-acid battery. The problem with a lead-acid battery is, of course, you're using lead, which is kind of a toxic metal for humans, so we have to make sure that we have safeguards in place to make sure that they are disposed of properly. Also, the electrolyte is sulfuric acid, and that is highly caustic, of course. And then corrosion is the idea that your metal that you want is being oxidized, right? Typically oxidized by air, and in this case, water is the conductor, right? It is conducting this this redox reaction. But what you see illustrated here is a sacrificial anode. So zinc is used to coat iron nails. They're called galvanized nails. And the reason why this is done is because zinc is more easily oxidized than iron is. And so you get zinc oxidized before the iron. And that's the idea. And then the zinc oxide layer actually provides protection for the iron against further oxidation. So that's the idea behind sacrificial anodes and corrosion. And then lastly, there's electrolysis. Electrolysis is the process of running an electrochemical reaction backwards by putting a voltage through the system. And when you do that, you are able to change a reaction that is non-spontaneous, and you can make it happen by forcing it the other way by adding energy. And so this is a common industrial practice. And in this case, this shows you how you get, they make sodium metal, like pure sodium metal. So you take sodium chloride solution and you melt the sodium chloride solution, which of course requires a lot of energy. And then you have to apply a voltage through the situation, and you get two things that are really, really dangerous by themselves, right? You get sodium metal by itself, or liquid sodium, even more dangerous than solid sodium. And then you get chlorine gas, which is of course toxic. So good times, good times. So that's the end. That's the last of the new content. And if you look back on the problem set, the homework problems, now you are able to do 54 and 60, and then I put 90 in there for fun. For success with 90, you're going to want to use the equations that you're given in your packet, because those are the ones that will help you to convert from grams of copper into joules, okay, based upon the cell potential here. Okay, so good luck, have fun, and let me know if you have any questions.